This is Learning Assessment Problem 920. The problem-solving strategy here is that of power factor correction in a complex load. We are referred to Learning Assessment Problem 916 for the data for this problem, and the original power factor was 0.84, and we wish to correct this to a value of 0.95 lagging using a capacitor which would probably be placed in parallel with the load. So we have a load power, real power of 40 kilowatts, and that will remain constant as we do this power factor correction. And we're given some other information. The load voltage is 220 volts, frequency is 60 hertz, and the transmission line impedance is not significant to us here because we are just working at the load end in this part of the problem. Since the real power in the problem will remain constant, we'll want to calculate the reactive or quadrature power for the original situation in the circuit, and then what will happen when we place the capacitor in parallel with the load. The original power factor, which we'll call PF1, is equal to 0.84, and that's the cosine of theta 1. And therefore we'll obtain that theta 1 is equal to the inverse cosine of 0.84, and that's equal to 32.86 degrees. Now we can calculate the original reactive or quadrature power. Q1 will be the load power divided by the cosine of theta 1, and then multiplied by the sine of theta 1. And this is equivalent to taking the load power and multiplying it times the tangent of theta 1. And this will equal 40 kilowatts times the tangent of that 32.86 degrees, or Q1 is equal to 25.837 kilovars. Now we can write the initial complex power, S1 we'll call it, is equal to the load power plus this quadrature power which we've calculated. So this is equal to 40 kilowatts for the real part plus J, 25.837 kilovars. Now we'll add a capacitor in parallel with the load. The new angle that we're interested in, theta 2, is equal to the inverse cosine of the new power factor, 0.95, and that's equal to 18.2 degrees. So the new reactive power with this capacitor in place is equal to the load power times the tangent of this 18.2 degrees now, and that is equal to 40 kilowatts times the tangent of 18.2 degrees, or Q2 is equal to 13.147 kilovars. Now Q2, the new value of the reactive power, is equal to the Q1, the original reactive power, plus the reactive power supplied by the capacitor, or the reactive power supplied by the capacitor is equal to the difference between the final reactive power and the initial reactive power, which is equal to the 13.147 kilovars minus the 25.837 kilovars, or Q capacitor is equal to minus 12.69 kilovars. The negative indicates that the capacitor supplies reactive power, and this is equal to, in terms of the capacitor value, omega C times the line or load voltage squared. The magnitude of that voltage squared is a minus sign in front of that expression as well. So the frequency was given as 60 hertz, which gives us a value for omega of 377 radians per second. Now we can calculate the value of the capacitance as minus Q capacitance divided by omega VL magnitude squared. It's equal to 12.69 kilovars divided by 377 radians per second times 220 volts squared, and this is equal to 696 microfarads for the required capacitance. You might note that this answer, 696 microfarads, does not agree with the answer given to the problem in the original statement of 773 microfarads. Apparently there was an error in the statement of which learning assessment problem to refer to. The 773 microfarad value would be the correct answer if the learning assessment problem 915 were used as the reference information.